And tonight, Helen will speak to us on the topic of Earth, our planetary life support system. So welcome, Helen.
Thank you, Sarah, and thank you for coming here. I don't know if for many of you, it's the first time you're in this beautiful, perfectly formed hall, but it really is a lovely place to be, and it's a lovely place to speak to both those of you here in the room and anyone watching online. So, the Earth. I spend a lot of my time thinking about our planet and how it works, and I like to start with this image because I think that we don't think about it enough. It's a very famous image. It's the blue marble from 1972, Apollo 17, when there was a moment, it was one of the few times during the Apollo mission when the Earth and the spacecraft and the sun all lined up. And so the astronauts could take a picture of the full illuminated disk of Earth. And of course, the thing about the Apollo missions was that I think people at the time thought we were doing it in order to go away. But actually, the thing it gave us was the ability to really look back and to see ourselves. And so for 50 years, we've had this image of ourselves on our home. And yet, our relationship with our planet is, mixed at best, I would say, at the moment. We don't really think of ourselves as citizens of this planet, and I think we are. And that's what this lecture series is all about, building towards a worldview, a framework that will help us all not just see ourselves as part of this planet, but see how our actions interact with it and what that means for the future and the choices that are facing us. So, taking the big view, that's what we're about here. So when I think about all of this, I think that each of us has 3 life support systems. We've got our own body, that's definitely a life support system. We've got planet Earth, and now in the modern world, we've also got the infrastructure of our civilization. So that means roads and transport routes, electricity supplies, all of these things that sort of happen behind the scenes, but also sometimes in plain sight, like bridges. And this is now also a life support system for us. And so the reason that I think we need to think about it like this is because our new life support system, our civilization's infrastructure, is increasingly clashing with the other 2. But they're all life support systems. They all matter. They all need to function. So we need to understand these relationships. And of course, we see our civilization clashing with health more and more as things like PFAS, forever chemicals, nanoparticles, microplastics, all of those things interfere with our own health. And we see it in the planet more and more as we humans have enough oomph to be shifting the levers of how our planet works. And so I think the great challenge of our time is to understand our planetary life support system and then learn how to work with it instead of against it, which it's at least some of the time what we're doing at the moment. So I think that understanding how the planet works from a really big point of view is a really useful thing, and it's something that we need to know as citizens of this planet, because we are an essential part of it. It's not that it's part of us. We are part of this. We should know how it operates. So the series of lectures that I will be giving over the course of this year are all on these topics. This is the first introductory lecture, big, broad, big picture thinking, and then the others will go through the component parts of the Earth system and look at how they work. So this is what we're all about today. Planetary life support systems. What is Earth? And because I'm a physicist, I think in terms of matter and energy. And so the big questions are what powers Earth and what's it made of? What can a sort of physics view, splitting the world into matter and energy, tell us about the way the world is? And then, of course, the last stage is how do we approach understanding it? Because that's not necessarily an obvious thing. So let's start with the big question, what is Earth? Now, there's lots of ways you can get an answer to this. How do we start on this question of addressing what is Earth? Well, the thing that a human does quite instinctively, because we're very visual creatures, is to look. And of course, it's possible to look in more than one way, but if we imagine ourselves arriving at planet Earth as if we were aliens coming from outer space, we can see here some of the views they might see. So the 2 on the left-hand side are pictures in the ultraviolet. That top one, you can see it's quite crude. That was actually taken during the Apollo missions with a relatively crude UV camera. The one below it is a more modern image. In the middle there, we've got visible light. So that top image of Earth is actually a new blue marble. NASA reassembled lots of pictures of a modern Earth to today, 50 years on. So that's the new blue marble. And then the bit that we forget is that actually the dark side of the planet also, you can look at that and learn things. And then on the far side, we see the world in infrared. So that's beyond wavelengths that are off the red end of our the spectrum that we can see. The top one's a false color image, so different types of infrared are portrayed in slightly different ways. And the bottom one is just an integration in black and white. And even from this, you can see that what we see depends on how we look. And so you have to be aware of how we're looking, because we're limited in how we can look. But of course, we've got technology to help us look in lots of different ways. So the question of how we look is not just about taking a picture in lots of different ways. It's also about the sort of things we're looking for, because Earth itself, just thinking about what's going on the surface of this planet for a moment, the bewildering, astonishing array of processes, very fast ones, very slow ones, very small ones, very big ones. All of these things are sort of mixed up together. So just to give you an example, just two random examples, they're not entirely random as you'll see, but two arbitrary examples of processes, the sorts of processes that are involved in our planetary engine. I'm going to pick out two. And the first one I'm going to pick out is something that's moving very fast, and this one is very personal to me. As you heard, I study breaking waves and bubbles out on the open ocean. And this video here on the left, we're looking up at the ocean surface from underneath as a wave breaks. And you can see that as the wave goes over the top, plumes of bubbles are generated very, very quickly. And then the bubbles rise to the surface, and then if you're looking from the top of the ocean, you can see these white caps, these white patches where the bubbles are brought to the surface. But the interesting physics that I'd like to draw your attention to here is the really fast processes that happen underneath the breaking wave, far too quick for us to see on this video, and far too fast for us to see with our own eyes. And so just thinking about this, you've got underwater bubbles, they're being smushed by turbulence, they're in a really complicated environment, so what happens to them? So this is a lab analog of the sort of thing that happens to bubbles underneath breaking waves. Those two tubes each have water coming out of them, so in opposite directions, and they're creating a region of shear where the water is going in opposite directions in the middle. And you can see that this bubble, which is about 3 millimeters in radius, is really distorted, and it goes into all kinds of beautiful shapes as it's distorted, and eventually it fragments into smaller bubbles. And actually, I think two of them are about to join together again. I can't quite remember. But this is just one bubble, right? And this is far too fast to see, and you can see how beautiful it is. And this is happening underneath a breaking wave millions of times. And the way it happens and the types of bubbles that are produced influence outcomes at the end. So this is like a tiny bit of physics that has all sorts of complexities built into it, but it's only one tiny thing. And of course, the time when it matters is when you scale that up. So the video here is taken from the back deck of a ship in winds that were about 60 knots. For those of you that operate in I'm not sure I got that right. I'm questioning myself about the 60 knots. I think it's 60 knots. Maybe it was 35. Anyway, huge winds pushing on the surface of the ocean. They are blowing the surface of the ocean away almost, pushing up breaking waves. And underneath those breaking waves, there's the turbulence, bubbles are fragmenting, and that's generating the white caps. So that tiny bit of physics that there was in the first video is being repeated billions and billions of times to create the environment that we see at the surface of the ocean. And it's far too fast and far too small for us to see directly. So let's shift focus now to a process that happens really slowly, that takes a long period of time to happen. It's again an ocean example, because I'm an ocean person, and this tiny little beautiful thing here is called a coccolithophore. So this is one of the ocean's sun harvesters. These are single cells. They live in the surface ocean, and when there's enough nutrients and enough sunlight, they build themselves and reproduce, and they sort of take calcium ions and lots of other things from the water, and they build these beautiful shells with all these little platelets. And it is a single cell. It's quite an incredible process. But when the conditions are right, billions of these can grow all at once. So many of them that even though if you were looking at a dish with one in, you couldn't see it. But when you put billions of them all together, you can see them from space. And so the light green in this image is you can see that they turn the water a slightly greenish color, and you can see the sort of swirls of mixing in the ocean that determines where the nutrients are. But the slow bit of the process is that when these grow very quickly, because the conditions change very quickly, the things that come along and eat them basically can't keep up. So there's lots of them left over that don't get eaten. They eventually sink down to the bottom of the ocean if the conditions are right. They layer up there slowly, 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 year after year after year. And if geology is on your side, they get compressed into rock, plate tectonics will move them around, and they may pop back up to something like this, which is the White Cliffs of Dover. So the White Cliffs of Dover are made of the remains of tiny, tiny creatures like this, accumulated over unimaginable periods of time, and they've popped up and created this rock. And the lovely thing about, chalk cliffs like this, so chalk, you heard at the start that people have been giving lectures at Gresham College since 1597. In all of that time, I bet there were a few along the way that used some chalk to teach languages, to teach mathematics, to teach history, writing it on a chalkboard with tiny, tiny ocean creatures that had lived millions of years before, which is a lovely thought. I'm a terrible artist, but it pleases me very much that even I can draw a coccolithophore with itself. That makes me very happy. But this very slow process is directly linked into our modern life. So to give you, and the way in which it's linked in is through concrete, not necessarily everyone's favorite thing, but if you're an architect, it's an artificial rock. You can make it into whatever shape you like. It's very useful. That might be the Sydney Opera House, or it might be the foundations and the core of New York skyscrapers. But there is a link, so let's see where it comes from. If you want to make concrete, what you need is cement and aggregate, which is just the kind of pebbles and the gravel. So cement's the important bit. So cement, if you want to get that, you need something called lime, which is calcium oxide. To get lime, you start with calcium carbonate, and the only concentrated source of calcium carbonate that exists on the planet comes from limestone. And limestone, one way or another, is collected, the calcium in it is collected by tiny sea creatures. And so every concrete foundation you've ever stood on, every piece of concrete you've ever put your hand on, a large part of the Sydney Opera House, quite a lot of the Pantheon in Rome, which is 2,000 years old, they're made out of tiny sea creatures that lived millions of years ago. So the point here is that the natural infrastructure is directly what we use to build our own infrastructure. And it's not just this example, it's all kinds of things. So you can see, or just from those two examples, the world is full of processes that are interwoven. They're different scales, they're different levels of complexity, they happen in different places, but they're all woven into each other. So if we want to understand the planet, what do we do? How do we manage all of this? Well, scientists like graphs like this one. So we've got time along the bottom on a logarithmic scale. So we've got 1 millisecond on the left, with a very small amount of time, and 30 years on the right. And then up the size scale, we go from 1 millimeter up to 1,000 kilometers. And you can kind of see that there's all that you can just think of processes. You can think of things that you might study if you want to understand the planet, and you can put them there. They've all got a time scale and a size scale. And it already looks complicated. And then you add in that our direct perception is only really this bit in the middle. So we're very good at ignoring slow, large things, and we're very good at ignoring small, fast things, because we just can't see them directly. So what I've set up here is a really complicated situation. We've got lots of processes in lots of places. They're fast and they're small and they're big and they're slow. And somehow we have to make sense of this all. So what is it that we do? And what we do is we look for patterns and we look for principles. The world, certainly the physical world, has very strong physical laws. And all of this operates within the bounds of physics, so that's all right. And we believe in physics that there are universal laws. We haven't had any evidence to the contrary yet. So, since there are universal laws, there are universal principles. And so our way of making sense of all this myriad of experience is to work out what are the patterns that are useful for understanding it, and to look at those examples and to see what we can learn about the world. So that's what this is going to be. This first lecture, I'm going to show you how physics leads you to some patterns, to some principles about how the world works. We're going to come up with 2 rules for how planet Earth works. And this is not at all to detract from the beauty and wonder of the world, because there's a thing where it's constraint that breeds creativity, right? If you give an engineer all the tools in the world and all the materials in the world and leave them in the middle of the field, they won't come up with anything interesting. If you tell them you can't do this and you can't do that, and by the way, that's very hard, then the creativity will force them to come up with something interesting. So these constraints on the physical world, as we will see, are directly what breeds all the wonder and richness of the world that we live in. So, I said I was a physicist, and I am going to follow the physics way of doing this by splitting this into matter and energy. And energy is the first one. One of the things that physicists do quite regularly in order to try and find some patterns and some principles is to draw a line around the boundary of something and say, well, let's consider what's in it and what's out of it. So we're going to do that with the Earth, draw a line around the outside and consider what is inside that boundary, that spherical boundary. And as I said, we're going to split this into energy and matter. And when it comes to energy, what matters is not just how much energy we have, but whether it can do something useful. And that is going to be very, very important. So let's look at energy. If you think about the energy that runs our planet, there's an obvious source, not perhaps, although maybe today the sun has come out, not so much earlier on today, but we know the source of energy to the Earth. It's sunlight. It pours in from the sun. It's a relatively simple source. What we don't talk about as much is that we're not just accumulating all this energy from the sun. That would actually be a really bad idea, because if that happened, we would just be getting hotter and hotter and hotter and hotter, basically. And the reason we don't just get hotter and hotter because we're accumulating lots of extra energy is because after a while we lose that energy. It's radiated away into space as infrared radiation, so heat energy, basically. So we can't see it directly unless you've got one of the cameras that showed the infrared image at the start. But there's this continual flow of energy through the Earth, in from the sun, and then slowly radiated away out into space. And the important thing is that, obviously, if you don't want the amount of energy on your planet to change too much, those 2 things have to be more or less balanced. The fact that there's energy coming in and energy going out doesn't say anything about the amount of energy that is inside the planet, that's inside this boundary. But that amount is what sets the temperature of the planet. So if there's more energy in the inside, what happens is it tends to end up as heat. We will see why in a bit. And if most of it resides as heat, that means if there's more of it, the temperature will go up. So we've got this balance between what goes in and goes out. And we can measure these numbers. So we know the amount of energy that comes in from the sun is very well known. The amount of energy that hits the top of the atmosphere is 343 watts per square meter of Earth. And we can actually now measure the energy that's going out. And it's a little bit less. We'll come to this in later lectures, but this is what's causing climate change. Climate change is fundamentally about us accumulating too much energy. We're slowing down the speed at which energy is lost into space, and so less energy is going out, and that means that energy is accumulating on Earth. So that's what's causing climate change. So there is an imbalance, which is generally a bad idea. We will come back to that in future lectures. But fundamentally, this flow of energy through Earth is what's running the planetary systems. Now, some of you might be thinking, but it's not the only source of energy. There's another source. We can easily think of one, and that's geothermal energy, right? We know that if you dig down into the Earth, if you go down a coal mine a long way, it feels hotter. The center of the Earth is hot. So how does geothermal energy compare with all the energy that's pouring in from the sun? Well, we can actually have a look at that quite easily. So the area of this square represents the energy that comes in from the sun. And I'm going to draw another box for the energy that is flowing outward from the center of the Earth. And it's tiny, right? Now, that's not to say it's not important. It does do very useful things like drive mantle convection and give us plate tectonics and all of that. But when it comes to running the surface systems of Earth, geothermal energy is very, very much smaller than the overall energy coming in from the sun. So we're mostly talking about solar energy when we ask what runs the planet. So then the question is, okay, we've got some energy, we've done the big picture, we can see stuff comes in, stuff goes out. How much of it is useful? How much of this energy can actually do useful things? Because that's what we want, right? We don't want energy so it can sit there and we can just look at it. We want energy because then it lets us do things, or it lets the planet do things. So in order to understand the cascade of energy through the Earth, we need to just look at a couple of bits of physics, and then we'll get to how this energy cascade operates. So the first thing is that, let's just think about these two pictures. We've got a pile of books, and we've got some books on the floor. Now, if I was to ask you to place a bet on the order in which these photographs were taken, you wouldn't have any problem with this, right? We know from experience that the image on the right with all the books on the floor is very likely to have been taken because the pile of books on the left fell over and became very disordered. And this is actually a very fundamental thing, that disorder in the universe always increases. It's due to the second law of thermodynamics. It's unbreakable. As far as we know, the total amount of disorder in the universe must always increase. And this is what gives us the arrow of time. We know that broken cups don't spontaneously reassemble themselves. We know that, very sadly, bedrooms do not tidy themselves up, right? You're always going in the direction of more disorder. So this is just the arrow of time going towards more disorder. And physicists have a mathematical way to describe that disorder, and it's the word entropy. So as far as we're concerned, it's just a measure of how disordered the universe is, and it must always increase. That's really important. Everything that happens, every single thing that happens anywhere in the universe for any reason, must increase the overall amount of entropy in the world. We'll get to what that means for the planet in a minute. But before we get there, let's just take another little look at the energy on Earth. So I said that there's energy coming in and there's energy going out, and then there's a kind of reservoir of energy that's sitting inside the planet. So one of the things about that energy is that it's not distributed evenly. And you can see an example of this. I mean, it won't come as any surprise to you. The temperature, the colors on the globe here represent the surface temperature of the ocean. And the reds are warmer and the blues are colder. And so you can see, no great surprise, close to the equator where the sun is directly overhead, you get a very high flux. There's more heat energy there, and there's less heat energy at the poles. Now, that matters a lot. It's not enough to have energy. You need a certain distribution before you can get it to do something. So let's have a look at why. We've got some color scale here. Blue's cold, red's hot. So let's imagine that we've got a bucket of fluid. It could be any fluid. Let's say it's water. And we give it a middling temperature, somewhere in the middle of that scale, so it's kind of purple. And then let's find another little bag of that fluid and put it inside. So we've got some warm water inside, some other warm water, and they're just going to sit there. Nothing is going to happen. Now let's take some water with the same amount of energy but distribute it differently. We will make the bucket cold, and then inside the cold bucket, we will put all the extra energy into the little bag of water. So now that's hot. And now things can happen because that little bag of water will have expanded because it's warm, so it will be less dense, which means that buoyancy will drive it upwards, and now we have movement. So the interesting thing about this situation is it's exactly the same total amount of energy, but in one case you get movement, and the other case you don't, and that really matters. And so in order to drive motion, you need what is called differential heating. So you need more heat in some places than others. So if you were ever thinking about complaining that, it can't be tropical everywhere, remind yourselves that if we had tropical weather everywhere on the planet, basically there wouldn't really be any weather. You're paying for having an interesting world with a little bit of inconvenience. It probably doesn't help if you're cold and miserable, but maybe it might for a few seconds. So now we've got the little bits of physics that we need to understand the large-scale energy flow through the Earth system. And it goes like this. Here's the energy that we've got from the sun, 343 watts per square meter. That's the amount flowing in. Now, not all of it gets inside Earth. Some of it is just bounced off the outside. So what we've actually got that enters the system is a bit smaller, 239. So what happens to it next? So then what we want is the useful energy. So it's not enough for its energy, it's got to be useful. So we need to look for the places where there's differential heating, where there's a difference between the heat in one place and the heat somewhere else. And that gives us a box that is a little less than half of that. This is the useful heat energy, the amount that can do stuff. And what happens to that is it can drive the weather, drives the atmosphere. The land and the ocean act like a hot plate, heating the atmosphere from below. And so you put energy into the atmospheric circulation. So that's kinetic energy. The air is moving. And then what that can do is blow on the surface of the ocean. And obviously, there's all sorts of little diversions from this. This is kind of the big flow. That can push on the surface of the ocean, which generates waves, as we saw before. So there's a little bit of energy goes into waves. And then once the waves have broken and that energy has ended up in the ocean, it can push on the ocean itself and drive oceanic motion. So that's kinetic energy that's in the ocean. So there's a large scale, there are lots of diversions, as I said, but there's this large scale flow of energy going through the Earth. Now, there feels like a problem here, right? Because it's getting smaller. And we were all taught at school that energy is conserved and it's okay. The rules of the universe have not gone wrong. But let's have a look at what the implications of this are. So we've got our, we're going to take another 2 buckets of fluid, always very useful for a physicist. So in this bucket, we've got some warm water underneath, cold water on top. It's not going to stay like this for long because the warm water is buoyant and it's going to rise. And then in this one, same amount of energy, but it's already mixed up. So effectively, it can't do anything. Nothing can happen. But the thing about this second bucket is that this one has higher entropy. So entropy is very useful here because everything that happens increases entropy. But then the process of increasing entropy makes energy less useful. So as energy is flowing through the Earth system, it's becoming less and less useful as it goes. And it winds its way down. It basically, the bottom of the cascade is that it will end up as heat that can't do anything. That's the highest entropy state. So the energy that comes from the sun is it's not disordered. It's a very structured thing. So that's low entropy. And then the energy trickles through the system, paying entropy taxes every time anything happens, until basically it all ends up as heat that can't really do anything at the bottom. So where we're going with all of this is that these energy flows through Earth bring us to an idea about what Earth is and how it works and what's actually going on here. So so there's our differential heating. Some is much more useful than the rest. That's the heat energy is left over. And entropy is always increasing. So what's this look like in the real world? Well, okay, so here we have a very nice picture of somewhere in Canada, I think. And in the middle, we can see a beaver's dam. And the thing about that is it's a highly ordered, organized structure. That beaver has spent a lot of time pulling twigs into the right place, moving them around, making sure it's just right. It's created something that is very, very ordered. And here's a cute beaver, being at work. So there's a question. So the thing is that in order to create that order, the beaver has to pay for it in entropy. It has to make the world around it it into a higher entropy state in order to pay for that dam being in a lower entropy state. And so what the beavers actually doing is just exporting entropy to the environment. And in practice, it's mostly making the environment a bit warmer. That's not really a big surprise. So you make your entropy low in there and you pay for it by making more entropy elsewhere. That's the way this goes. So the beaver's just an entropy pump. That's what it's doing. It's creating order and paying for it in entropy. So the question then is, and it's quite an interesting question, is where's the boundary? So here's a beaver. That's all right. Let's do our physics thing and put a little border around the boundary. And so the beaver itself has all kinds of ordered things going on its insides. You know, it's got to keep its organs going and it's got to digest its food. And all of this is ordered and organized. So it has to pay for it by exporting entropy to the world around it. But then we just saw that the dam, outside itself, the beaver can create something which is ordered. So it's increased order outside itself. So that's no good, is it? Because there's more entropy, but it's outside the beaver. So where do we put the line? If there's an inside which is becoming more ordered and more structured, and an outside where you have to make disordered, then where's inside and where's outside? And the logical endpoint of this argument is the planet Earth. That line we saw at the start that goes around the planet is the only sensible place to put the boundary. So we create all these beautiful organized structures on Earth, and we pay for it by pushing entropy outside this line. And this is where the Gaia hypothesis came from. Many of you will have heard of James Lovelock, the scientist who did many things, but scientists know him for inventing the electron capture detector, which is very, very useful for detecting CFCs and things like that. Everyone else knows him because of Gaia, the Gaia hypothesis. And he started off thinking about how do we detect life on other planets, and he started thinking about entropy. It's like, well, if there's life, there must be something playing this game of exporting entropy to the universe. And where do we put the boundary? And you can actually see it in one of his early papers on this. You can almost see him thinking this through, that he says that if instead of individual living organisms, the planetary ecosystem is the unit of life, then this whole problem goes away, that it's the planet that's exporting entropy to the universe in order to have all these interesting structures on the inside. And so the original version of Gaia implied that somehow the planet was intentionally doing this, which is not what we think of Earth system science now. Now we think that there are feedbacks, which we'll come back to in later lectures, and structures which basically maintain things, but the outcome is the same, that we are basically living in a delightful, rich, complex, ordered world, and we are paying for it by exporting entropy to the universe. And so the important thing about the energy trickling through Earth is that even though the amount of energy that comes out is the same as the amount of energy that goes in, what goes out carries entropy with it, and that's how we pay for our world. And this is the sort of scientific way of expressing that the light that comes in has shorter wavelengths, higher energy, fewer photons, so that's a low entropy state. It passes into the Earth, and there's a load of irreversible processes that create us and everything else, and then energy goes out, but now the energy that goes out is at a longer wavelength. It's far, far more photons, and so we've exported entropy to the universe. And so this is a different way of thinking about how energy flows through the planet, because it puts limits on how much of that energy is actually useful, can actually create a structure. And it means that although in theory we do have a vast amount of energy from the sun, we have to be a bit more careful than that, because not all of it is useful. But all of this guides how it flows through the planet. So we're going to come back to some of this later, but I think it's a really fundamental idea. So having dealt with the physics of energy and Earth paying for beauty with entropy, which is where we've got to, let's have a little look at the matter. We've done the energy, let's have a look at the matter. So although energy flows through Earth, which implies that Earth is an open system. Energy can cross this boundary that we drew here. That's not true for matter, with like tiny exceptions here and there, meteorites and things like that. The atoms that we've got on Earth are the only ones we've got. They don't escape this boundary, they just stay here. But that's all right, because there are an astonishing variety of them. I think there are 94 naturally occurring elements, which is astonishing variety. The vast majority of the universe is made of hydrogen. About 23% or so of it is made of helium, and then there's this tiny other fraction of weird stuff. And our planet is made up of the weird stuff, which is really useful because it means it's got lots of variety and you can do lots of different things with it. It's no fun if all you have is a Lego box that's just got single blocks that are all the same. I mean, you can do some things with it, but it's pretty limited. So there's loads of variety. The elements on planet Earth are many and varied, and this chart shows the numbers of atoms by number. So it's not by mass, it's the actual number of atoms. And you can see that actually most of our planet is iron and oxygen with a bit of silicon and magnesium and some other stuff. So even though I said we've got 94 elements around, the interesting ones are definitely in the minority. This is mostly a planet of iron. But of course, all of this is not equally accessible to us. It is one of those continuously astonishing things to me that even though I am part of a planet that is 1/3 iron, it is still possible for me to be anemic, which is just rubbish, right? And the reason is partly that a big chunk of that iron is in the core of the Earth, so it's away from me, but also a lot of it is chemically inaccessible. So we get into, there's a lot of subtlety there in how things move around. But anyway, so we've got lots of different types of atoms. So basically, Earth has existed for billions of years. And what this means is that recycling isn't just necessary, it's inevitable. The only way to go is for stuff to go round and round. But the humans have not always appreciated this. Humans have frequently forgotten that the recycling has to happen. So this is I want to tell you a story that's an example of this. The cross there is more or less where Sydney is in Australia. So Australia was colonized by Westerners who came along, and the first fleet arrived in 1788 with convicts, and they were all set up to live in Australia. They just arrived. And it wasn't just convicts, actually, it was also cows. The people who came to Australia, first of all, brought a lot of cows. And when I say a lot, I mean a lot, like just loads of cows. So this plot shows just the number of breeds, not even the number of cows. And you can see that in 1788, there was one breed and, a few cows. And then people just kept bringing more and more and more cows. And then they got really inventive and they started bringing all kinds of cows. And Australia was basically filling up with cows, but it came with a problem. And the problem was the cow pats, because cows obviously produce a lot of cow pats. And the problem is that in Australia, the local wildlife, wallabies and kangaroos and things like that, koala bears, they're all adapted for a dry place. That means you hold on to water. You don't go just squandering it in your poo. That would be terrible. So everything that lives in Australia makes basically extremely small, hard, dry poo. And all the local beetles, dung beetles and insects, they're adapted for that. They can deal with that. So the problem when the cow pats came along was that nothing in the local fauna knew what to do with it, so it just didn't. So the cow pats built up, and instead of lasting for perhaps a week or two, they were lasting for months and years, just sitting there. Australia was filling up with cow pats. And this situation continued. And what was happening here is that basically no one was doing the recycling, right? There's loads of nutrients in poo of all kinds. But in order to move them along so they can be used by something else, you need to move them through a process, right? You need to do something about it. So no one really resolved this situation until about 1960, when someone turned up and he said, well, other places have beetles and bugs and things that can deal with all with this. So that was the start of the Australian Dung Beetle project, which began in 1965. It ran for 20 years. I promise I'm not making this up. They introduced 43 over the years species of dung beetles. It was actually a very careful scientific process. They looked for things that weren't going to compete with the local wildlife and weren't going to cause any problems or bring diseases. They tried all these different beetles. 23 of them sort of stayed. And the biggest direct benefit to Australians, the reason the government paid for this mostly, was that the wet, sloppy dung was really, like, bush flies loved it. So there were huge plumes of flies everywhere. And so once you've got some dung beetles, the right kind of dung beetles to deal with the wet, sloppy cowpats, then you start to have far fewer bush flies and humans get much healthier. And then the nutrients are recycled back to the soil. So you've then got a recycling process. They restarted it actually in 2017 for 5 years. And this is their website, and I really like the tagline, Beetles with Benefits. Because the point is that as humans, when we look at nature, because nature is so good at recycling, we often assume that it's just going to happen automatically. So although recycling is essential, these atoms have to go round and round. It's not automatic. So nature has evolved its own processes for this. Humans haven't necessarily realized that it's not just magic. You do need a process. But of course, when evolution has had a long time to get used to all of this, then you do get beautiful systems, and waste becomes a resource instead of just stuff. So just in the ocean here, just as an example, we can see the kind of food chain that we were taught at school. You've got phytoplankton, like those little coccolithophores at the top. They take energy from the sun, they build themselves, they feed the zooplankton then get eaten by the fish. The nutrients, which are the important bits, get passed down the chain. And then these animals will all poo. And for various reasons, nutrients in the ocean tend to sink downwards. So all the good stuff's going downwards here. Things die and sink to the bottom. So the nutrients are all going down to the bottom. There are various ways in the ocean of bringing it back to the top, but one of the most memorable is the whales, because the whales feed slightly below the surface. The seal's just busy dying over there. The whales feed below the surface, but when they come back up to the surface to breathe, they also defecate. And so they then deliver nutrients back into the top that can then find their way back down the system. And the reason that my whale poo there is red is because it really is. And the reason it really is because it's really rich in iron, especially in the Southern Ocean. This is actually quite a constipated whale. Whale feces is normally much more liquid than this. But the point is, it's full of iron. The iron is being recycled around the system. There are other ways to do it, but whales definitely contribute to this. So waste becomes a resource. It becomes the start of the next thing, not just an endpoint. And so where we've got to with all of this is that, and fundamentally that's because matter is conserved, right? There's conservation of energy and there's conservation of matter. So we've arrived at the two rules for planet Earth, the two unbreakable rules for planet Earth. The first rule is that energy flows through the system, but it becomes less and less useful as it goes down the cascade until eventually it's radiated away into space. And what that means is that we pay for our beautiful, rich, complex, ordered society by giving the universe more entropy than it otherwise would have had. And the second rule is that the atoms have to go round and round, but they need processes to get there. And so this is what makes Earth a rich and complex place, because you've got a continual flow of energy through, and it's doing things to all these atoms. It's organizing them. It's creating structures, and that's why the world is beautiful. So as citizens of Earth, how should we think about all of this? The first thing is we're part of this. We're clearly not separate to it. We can't draw a line around ourselves and say, this is us and that's the planet. The whole thing is connected together, and we are part of that woven fabric, which is a beautiful thing to be, to see those connections. And it's also very humbling. Like, a lot of this exploration of nature comes with the idea that there is a massive engine that we live inside, and we at least, both for survival reasons and for just living a good life, we need to understand that engine so we can see how we're part of it, because it's a beautiful thing. We should celebrate it. So this big picture, I think, is a really useful way to look at planet Earth, to understand what it is we're part of. So where we've got to here, we can see the summary here, that we can see it from lots of perspectives, but all of them are valid. That's the important bit. There's always a new perspective, and you will learn something if you look at the Earth differently. So there's no one way to look at our planet. It is highly interconnected. This is all about connections. Energy flows through the Earth, stuff goes round and round. We pay for beauty in entropy. And this is the big picture of the planet. So what happens next? Well, the thing is that all of that structure inside the Earth has given us different systems. It's easy to split it into the atmosphere, the oceans, biology, rocks, and the ice. Rocks and soil and the ice. And so then the next stage is to go slightly inside the Earth system and to look at the rules and principles that guide these parts of the system as we build up a bigger picture of planet Earth. But that is all to come in the lectures for the rest of this year, and that's it for today, so thank you.